Let me share my screen. Everybody, can you see my screen?
Yes.
Okay. So this is the midterm exam question. Um, so I mean, you have done well, most of you, although there are some mistakes in some cases in numerical problem or answering to the theoretical question. So I'm just going over. The first one, you see, what is the disadvantage of an unbalanced power generation system? So you all have written differently. So main thing is that once there is any unbalanced in the system, basically there could be the voltage difference between two phases. So there will be circulating current flow. And if there is circulating current flow, that will generate some heat. So system might be heated up. Then in addition, if there is any unbalanced situation, then there will be some current flow through the neutral, provided that that is the Y connected system. So, for a Y connected system, definitely there will be neutral. So, if there is any unbalance, then zero sequence current flow through the neutral. Probably you remember that in the class we discussed about zero sequence current that flows through the neutral. Therefore, depending on the value of the current, neutral might be overloaded. So, neutral might be burnt or cut. Or even if it might not be burnt, but the neutral current will start flowing through another neutral of any neighboring device. So those are the issue of the unbalanced system. So therefore, main thing is that there could be circulating current flow as well as there can be zero sequence current flow through the neutral, especially of the Y connected system. So those will cause some heating, even the system might be burnt. Now, question number B, write down the three-phase active and reactive power equation for an unbalanced load. So therefore, you see this is unbalanced load, but many of you have written down the equation for balanced load. Like you just wrote root 3 VL IL cosine theta and root 3 VL IL cosine theta. But that is wrong. That is not, that is for the balanced system, balanced load. So when the system is unbalanced, it is not, you cannot multiply by 3 or you cannot multiply by root 3. So you have to calculate phase by phase, on phase at a time. Therefore, your power equation will be, for example, for phase A, VA IA cosine theta A, then plus VB IB cosine theta B, then plus VC IC cosine theta C. Similarly, the reactive power equation, VA IA sine theta A plus VB IB sine theta B plus VC IC sine theta C. Everybody, could you follow me?
Yes, so far, yes.
Yeah. So therefore, see your, I believe you have your hard copy of the exam with you, or if it is not ready, I mean, later you see. And that's why accordingly, so the thing is that the full credit was 100, and then you see there are total 7 questions. So therefore, 7 multiplied by 14, it becomes 98. So that's why for question number 1 and question number 2, I have given like 15 credit, like 15 credit for question 1, 15 credit for question 2, and then remaining from 3 to 7, 14, 14 each. So in that way, it is total 100. Accordingly, in the feedback location, when I have given my comment, I have mentioned, okay, your question number score is 14 or 15, question number to this, and then you sum up, that is your total. So therefore, depending on where you made mistake, accordingly, I have got sometimes 2 credits, sometimes 3 credits, sometimes 1 credit. In that way, accordingly, I have got. And you see there is like A, B, C. So of course, the major credit is for the part C, the numerical problem. but depending on where you made mistake, either B or A or something in C, accordingly I have got credit. Okay, now everybody see the problem. I mean, most of you have done this problem correctly, but still there is some mistake. We did on exactly, I think, similar problems in the homework, but homework problem was about delta connected. In this case, it is Y connected, that load. That's only the difference. So now see, first I am calculating the current. So this is the generator. It has the 6 MVA capacity, 60 Hertz system, and that is powering a Y connected load. So therefore, I have drawn a brief schematic. This is the load. It has 6 MVA with 0.85 lagging power factor, and 8410, that voltage was given. You see, 8410, that number was given here. So first from here, from the load side, I'm writing the apparent power equation, S equal to root 3 VLIL. And then that VL is this one, 8410, line to line voltage. And then I am getting IL 411.9. And power factor was lagging 0.85. So this is the cosine theta. From there you calculate theta. Theta is 31.79 degree. But I am putting minus sign because this is lagging power factor. So then you go, the question was find out the total complex power absorbed by the Y connected load and the total the load impedance per phase for any of the phase. So therefore you see complex power root 3 VL IL conjugate. So therefore VL is fine as it is 8410, but IL, this is your IL and you conjugate it. So that's why it was minus sign here. I put the plus sign. And then you calculate. So in terms of kVA, it is 6 at an angle of 31.79 degree kVA. Or you might express in rectangular form. That is also correct. Many of you have converted into this plus J something. That is also right. And then come to that impedance per phase, load impedance per phase. So you just need to know what is the voltage across each phase. Now, because this is Y connected system, you see, this is the Y, and this is the line to line voltage. So phase voltage will be line voltage divided by root 3. And because this is Y connected system, therefore your phase current and line current is the same. Therefore, we already got the line current here, this amount. This means here is the line, but it is the same through the phase. So therefore, GLP, load impedance per phase, that you see 8410 divided by root 3, and then that magnitude, this magnitude. And then I did not include the angle, but you could include this angle. So therefore this will be this at an angle of this one, 31.79 degree. But the magnitude will be this. Therefore, you see your calculation, sometimes you got completely different result. I noticed that sometimes you did not divide this one by root 3. You kept this one as it is, but then you divide this one by root 3. That's why you got completely different result. So you see, you have to look that this is the Y connected. In the homework, we solved considering the delta connected. So if it is delta connected, then this is fine. We have to divide here, but this is Y connected. So is everybody fine?
Yep, sure am.
Yes, great. So everybody see your, and accordingly, you see the question number where I cut your credit 1, 2, 3, depending on situation. Okay. Question number 2, reactive power is of no use. Then why is reactive power control needed in a power network? So you see that if you don't control the reactive power in the power network, so meaning that your system will have low lagging power factor. Therefore, reactive power basically provides low lagging power factor. Consequently, there will be huge voltage drop in the system there will be huge reactive power loss, and your system efficiency will be low, as well as voltage regulation will be poor. That's why, even though reactive power is of no use in practical life, but still we have to control it. So that will be the appropriate answer. So therefore, like once again, if you don't control the reactive power, then your system power factor will be fairly low lagging. That will cause voltage drop. That will cause much losses, especially the reactive loss, like I square XL loss. And this means that your voltage regulation will be poor and your system efficiency will be low. So that's why we have to control the reactive power. Therefore, most of you have written differently, but I have taken your answer um, depending on situation. If it is not proper or appropriate, then I have got 1 or 2 credit, as you can see. And then question number 2, again, most of you have done properly, but in some cases you got different result. I don't know why, especially this power factor. Instead of 0.93, some of you have got 0.98. So I don't know where you made mistake. So therefore, once again, quickly have a look. The first you see that load power is given 298 kilowatt. So first I am writing phi equal to Vi cosine theta. This is the single phase system, and you plug in all the number, voltage, current, but keep in mind voltage in kV, 2.5 kV that I'm indicating, so that you don't assume that this is just the volt. So therefore I got cosine theta approximately 0.67 lagging. So this is the first answer. What is the uncorrected power factor? Uncorrected means before installing the shunt capacitor. So that power factor 0.67. And then from there, I am calculating sine theta. I first find out theta and then sine theta. And then the next question is find out the reactive load. So therefore, I am finding the reactive load Q Vi sine theta. So again, those values are given. This is the sine theta. And then I got 329.3 kilovar approximately. So many of you have directly written 330 kilowatt. That is also okay. And then the next question is, what is the new corrected power factor after installing a shunt capacitor unit with a rating of 210 kilowatt? This means this is the improved power factor or new power factor. So you see, I have just shown this one. So you might not show this power triangle, but what is your Q new? So this is the amount that is being provided with that uncorrected power factor. This means this is your Q word 329.3, and capacitor is providing 210. Capacitor is giving you 210, this one. So I'm subtracting that one. This is that amount. So my new Q is 119.3. So therefore I got a new triangle. This my phi is as it is. This is my new Q, and I got a new angle which is theta nu. So therefore I am finding Q nu over phi, which is tangent theta nu, that is 0.4003 approximately. From there I am getting cos theta nu 0.93. So this will be the right number approximately. So therefore I don't know like how you got 0.98 sometimes. Is everybody fine? Therefore, you match with your hard copies of the exam. So I believe you are keeping, and then you see where you made mistakes or the that first question, theoretical question, is not appropriate enough. Accordingly, I have got some credit, 1 credit or 2 credit, 3 credit, depending on situation how you answered. Okay, then moving forward, question number 3 was, what are the objectives of open circuit test and short circuit test of a transformer? So Therefore, I mean, most of you have written down properly. Sometimes you wrote something deviated. Uh, the open circuit test means its objective to get the core loss or constant losses. And then objective of the short circuit test is to get the copper losses or the variable loss. So in addition, you can find out the equivalent circuit parameters. So sometimes some of you have just written that, okay, those two tests help to get the equivalent circuit parameters. That is fine, but still you have to mention the main thing that open circuit test provides the core losses or constant losses, and short circuit test provides the copper losses of the transformer. And now this problem, so many of you have done properly, but some of you have done completely differently. So you got completely different result. You see, determine the primary induced voltage of a 60 Hz transformer having primary number of turns upon 10. Assume the mutual flux waveform can be expressed as phi equal to 12 sin omega t milliweber. This means that 12 is the magnitude, 12 milliweber. That is the phi m, mutual flux. Also, if the primary coil has an inductance of 1.8 Henry, then calculates its magnetizing current. So therefore, for the first part, for any primary induced voltage or secondary induced voltage, you remember this was the equation of course, this was in RMS quantity. So E 4.445 Fn, and then you just plug in those numbers. So you should be getting approximately this number, 351.648 volt. And once you get that, then many of you have not done this one. Either you left blank or you did completely different thing. Yeah? Not this thing at all. So this is the relationship. L equal to N phi over I. I mean, of course, this is the phi A mutual flux. And then you are asked to calculate magnetizing current. This means this current I. So then plug in those numbers, and L value is 1.8. So result is 0.73 ampere. That is that magnetizing current. So is everybody fine?
It's the turns times the magnetic flux for that one.
Yes, yes. Actually, in the same, you could use the symbol phi m to indicate the mutual flux. So again, that is the same flux, which is this one, the 12 milliweber. So
Okay.
Moses York, I think you are Moses York, right? Yeah.
Yes, correct.
Yeah. From your voice, I guessed. Yeah. So what's your question again?
No, I was just making sure that that was the mutual flux for it.
Yeah, that is mutual flux. So therefore, in the statement, you see, it's clearly said, assume the mutual flux waveform. And then in the symbol, I think in the class when I derived this theory, I said phi equal to phi m sine of omega t. Although I'm writing just phi, but this is phi m. And then the L value was given 1.8.
Perfect. That makes sense. Thank you.
Okay. The question number 4. Draw the approximate equivalent circuit of a single phase transformer. So most of you have drawn this properly, although in one or two cases, you did not show either primary or you did not show that mutual flux thing, but in most cases, you have done this properly. For the numerical problem, again, most cases you have done properly, but again, in some cases, there is some mistakes. Let me go over it. So once again, everybody see. A two-pole squirrel cage induction generator is connected to a 4.16 kV distribution grid and is driven by a 3.2 horsepower motor that develops a torque of 7.5 Newton meter. If the slip of the generator is minus 0.012, then calculate the grid frequency. Also, how much reactive power will be drawn by an inductive load of 2.2 Henry connected to the Great. You see, I have drawn a brick schematic. This will be the schematic. This is that SCIG, squirrel gauge induction generator, see, and then that is powered by a motor because it requires the prime mover, because you have to make the slip negative. That's why you need prime mover. So in this case, whatever the type of the motor is, whether it is DC motor or synchronous motor or any other type of motor, you need it. And it has these specifications: 3.2 horsepower and 7.5 Newton meter. And both this motor and the induction generator, they are sharing the common shaft. That's why I'm saying this is on common speed. This means if you can find out the speed for this motor, that is the speed of the induction generator. That is the meaning of this symbol. And then that generator is powering a grid. At this point, voltage is 4.16 kV. One thing I think I made on mistake, I should say, as single phase induction generator. This is basically single phase induction generator. This is not that. I think I forgot to write. But most of you have considered this is the single phase. I think only one case you considered. I think probably Alexandria, you assume that this is the three-phase generator, right?
Yeah, I guess so.
Yeah. I remember because you divide
Yeah.
this by root 3. Yeah.
Mm-hmm.
To
Yes.
get this QL. This means then I looked at why you did, then probably you assumed that this is the three-phase. Yeah.
Mm-hmm.
Right. No, I understood why you did that. I figured it out. But everybody assumed that this is single phase. But even though I did not mention single phase or I did not mention three phase, but this will be single phase. I mean, this is my mistake from my side. Anyway.
I understand. Thank you, though.
Yeah.
Mhm.
So therefore, everybody see the first of all, the from here, from motor 3.2 horsepower and 7.5 Newton meter, you calculate the omega. What is the speed of the motor? So you see, I am doing omega P over tau. So 3.2 horsepower, and then I'm multiplying by 746. 7.5 was the Newton meter. So I got a speed value in terms of radian per second. And then here I am converting it into RPM. So this means I am using the symbol NR. If you see the slip equation for this squirrel gauge induction generator, slip is NS minus NR over NS. So therefore this NR is this one, 3039.48 RPM. Now this is your slip equation. Slip value was given minus 0.012. You substitute that value in that equation and NS minus that one. So ultimately you got NS this number. And once you got the NS, then NS is 120 F over phi. Pole number is 2. You see the pole number 2 that was given. So therefore ultimately I just approximated, like you got 50.3 something or 50.0 something. Just I took the round number 50 hertz. And then once I know the frequency, then you are able to calculate how much reactive power is being drawn or being consumed by this inductive load of 2.2 Henry. So that's why QL is VL square over XL. So my VL is 4.16 kV, and then I got 0.025 megavar, or you have expressed 25 point something kilowatt. That is also fully right. Is everybody fine? Could you follow me?
Yeah, definitely.
Yes. I mean, most of you have done this properly. In few cases, 4 or 5 cases, there is some mistake. You got completely different result. And you're both like frequency and then Q value is fully different, much deviated. So therefore, what I'm going to do after the class, I'm going to upload this solution on eCourseware. I mean, you will see a midterm exam, the exam tab. in that tab, under that tab, I am going to upload as, for example, solution for midterm exam 1. I will convert this one into PDF file and then I am going to upload. So again, you can see those things. Okay, fine. The number 5, what is an auto transformer, and mention its application to a power network. So therefore, almost everybody have written this properly. So auto transformer means that that same winding that will be shared by both primary and secondary, that you have properly mentioned. And application means mainly it is used high voltage lines with 2 different voltage for interconnection purpose. This means auto transformer interconnects 2 transmission line having different voltages. And then this problem, for short circuit test, open circuit test. Here, sometimes you have done properly, sometimes you got fully deviated result. I don't know why. And then also determine the efficiency of the transformer. I think the result should be about 99.1%, but again, you got completely different result. Even some of you like 102. So I don't know how that happened. So here is the calculation, you see. From the open circuit test parameter, test data, first I am calculating YOC, admittance for open circuit test from these data, open circuit test data. And then I got this thing 1 over RC minus J. So I got RC value 88.57 kilo ohm and XM value is 3.695 kilo ohm approximately. So some of you have expressed in ohm, that is fine, that is fine. But then sometimes you got completely different result. Probably you messed up somewhere in converting polar to rectangular or something, or with the angle you messed up. So your angle is coming 87.61, but you have to put the minus sign, being the fact that transformer provides the lagging power factor. Okay, that is fine. And you see, then with the short circuit test data, these 3 are the short circuit parameters. I am calculating GSC, VSC over IC. In this case, my angle is from here 71.33. And then it went in the numerator, it became plus. And so I got 0.69 plus J 2.046 approximately. So this means first part is the R equivalent plus J. This is the X equivalent. And then, so sometimes some of you just ended up here. You did not again further go ahead. So you should go ahead and calculate R1, R2, X1, X2. I mean 6 parameters, R1, R2, X1, X2, and these 2 core loss component, RC, and then magnetizing branch component, XM. These 6 are called actually the equivalent circuit parameters. So many of you, after this line, you did not move forward. So you see that we had an approximation that for a well-manufactured transformer, R1 equals to A square R2 equal to R equivalent by 2. So A was the turn ratio. So sorry, the 10 was the turn ratio. That's why I have written A is 10. This, where is that number? This one, 2400 over 240. This means this is the 10 turn ratio. And then if you do that, so R1 is 0.345 ohm. R2 is 0.00345 ohm. So you see your answer. Sometimes you got completely different result. Here you got like several hundred kilo ohm. In that way, you mega ohm, even you got. So completely you did wrong thing. Even though you calculated A10, but then still your result is completely different in many cases. And then you see X1 A square X2 X equivalent by 2. So X1 should be 1.023 ohm approximately, and X2 is 0.01023 ohm. And then efficiency should be 99.11%. So is everybody fine? Do you have any questions, confusion?
No, makes perfect sense.
Yes, please everybody just match with your note. Yeah. Okay, fine. Then moving forward. Question number 6. What is the difference between AC excitation and static excitation of a synchronous generator? So therefore, this is the synchronous generator question. So you remember that in the class we discussed there are 3 types of excitation to magnetize or to excite the field. One is called AC excitation. So AC excitation means you have a small size of AC generator mounted on the same shaft of the main generator or of the field. So, and then because this is a small AC generator, but the field always requires the DC, so there is a small reactor, and that reactor is converting into DC, and that DC is being provided to the magnetic field. So that is the AC excitation. On the other hand, static excitation, this means that you have your 3-phase terminals, static terminals, armature terminals or stator terminals, which is static, not rotating. And then you are taking that power to a rectifier, and then that rectifier is converting into DC, and that DC is being supplied or being provided to the DC magnetic circuit of the field. That is the static excitation. So in this case, it is called static because it is not a like AC generator or even a small DC generator. Output is being taken from the static terminal of the stator or the armature, and then converted into DC and then fed to the DC magnetic field. And AC excitation means there is a small AC generator that is mounted on the same shaft of the magnetic field shaft. So that is the difference. So sometimes many of you have written properly, sometimes you have written completely different thing based on your understanding. Okay, now the problem, calculate the shaft output power and the efficiency of a 3-phase 208 volt 25 horsepower induction motor that is supplied with 75 ampere at a 0.85 lagging power factor. Its stator and rotor copper losses are 1867 and 650 watt respectively. The core losses at the stator and rotor are 750 watt each. The friction and windage losses are 300 watt, and the stray losses are negligible. So the question is find out the shaft output power and then efficiency. So answer should be efficiency should be 81.2 and shaft output power should be 18.65 kilowatt or 18,650 watt. But I noticed sometimes you have got 9,000 something, that is wrong. And then here you got like 83 point something, some cases. I think kind of about 50-50. 50% is to you have answered properly, you got exact result, and then in other cases, you got 83 and here. So probably you made mistake somewhere here, yeah. But I looked carefully your calculation. Accordingly, I have got 1 credit, 2 credit, 3 credit, depending on situation. Therefore, first I am calculating that input power √3 VL cosine theta. This is clearly the 3-phase. It is mentioned 3-phase system. So that's why you have to use this equation √3 VL cosine theta. And then I am plugging all those numbers given 208.75. I got 22,967 watt approximately. And then, I mean, although you have directly calculated, you might directly calculate in online, that you are fully fine that you did. I'm just showing you step by step for your understanding. Next, I am calculating air gap power. And so this means this is the input power minus stator copper losses minus stator core losses. So both are stator quantity. So therefore, stator copper losses on 867 and core losses is 750. So I am subtracting that. I got 20,350 watt air gap power. And then next I am calculating mechanical power, because this is air gap power is the input to the rotor circuit. So then I am calculating mechanical power. So this means air gap power minus, this is the rotor copper losses This is the rotor core losses. So you see, then 650 watt was the rotor copper losses, and then 750 watt each. It was the same for both stator and rotor. So that is my mechanical power. And then from the mechanical power, I am calculating the shaft output power. This means this minus, I think, the friction and windage losses are 300. And there was no value for the stray losses. It was negligible. That was 0. So finally, I got 18,650 watt, or you could say 18.65 kilowatt. And then find out the efficiency, this ultimate output, eventual final output, over what is the original input. This was the original input, actual input to the motor, electrical input, and then percentage 81.2. So is everybody fine? So therefore you see that sometimes you got 83 and sometimes you got 19,000. How you got that one? Probably somewhere you made mistakes in subtracting. So something you messed up. That's why you did not properly get this thing. But many of you have properly got this one. So is everybody fine?
Yeah, we're good.
Yeah, okay. So please look, and then once again, I am going to upload this on eCoursera, as I said, under the exam tab. Yeah, you will notice. Yeah. Still, I did not, but I will do. Okay, so the last question was, suppose you have a three-phase induction motor in hand, but you need a generator. Is it possible to use that motor as a generator? Explain your answer. So the answer is yes, it is possible. Just keep in mind, not only this is true for induction motor, even in case of synchronous generator, if you have a synchronous motor, then you can convert into generator, or you have generator, you can convert into motor. It's just the mode of operation, how you are using it. Same thing goes for DC motor, DC generator. It is the same machine, same device. Sometimes you could use it as a motor, sometimes generator. It depends on mode of operation. So for this specific question in the exam, so answer is yes. And then when I am saying the explain your answer, you know that the difference between induction motor generator, you have to make the slip negative. This means you have to increase the speed, rotor speed, and that rotor speed should be greater than the excitation field speed or the synchronous speed. So therefore, first you say, yes, it is possible to use that modern generator. And then to explain your answer, say that to run as a generator, the slip should be negative, and that is possible by increasing the speed of the rotor. The speed of the rotor should go beyond the synchronous speed. This means you might need to connect an external auxiliary prime mover, some other motor, like some wind generator or something that will make your speed, rotor speed, higher than the synchronous speed, and ultimately will cause the slip negative. So that will be the appropriate answer. And most of you have written the answer properly. In some cases, there is like few mistake. And then, why is a capacitor bank connected at the terminal of an induction generator? Again, most of cases you have written properly, but sometimes you have written very briefly and something different. So you see the in case of induction machine, whether it is generator or motor, always it draws reactive power from the system. That is the basic nature. It draws reactive power from the system. That's why even though at steady state situation or normal situation, the power factor becomes low. Consequently, there will be voltage drop at the terminal. Now we have to maintain a constant voltage. You have to maintain a constant power. In other words, rated power and rated voltage. In order to maintain that rated voltage and rated power at the terminal, or in other words, to compensate that reactive power which is required for the motor operation, you have to insert, you have to connect a capacitor. That capacitor will improve the power factor and it will maintain the required voltage. That's why capacitor is always connected at the terminal of the induction generator. So therefore, we have written something different. So many of you have written properly. So but please note down this one. Is everybody fine?
Yes, I am. Yes, so far.
Yes. So Moses, therefore, I'm going to upload these things. I will convert just PDF right after the class. And again, I'm saying I will be uploading. And then once again, you look and you check with your answer that you did with that hard copy of the exam. And then maybe still, if you have any questions, confusion, and then you please let me know. Then I will reevaluate you. Okay, so is everybody fine? Do you have any question, confusion, anybody? Therefore, you see in the feedback location on that Dropbox, I have just written some brief comment. And I have given your credit for each question. Question number or this 14 or question number 210, question number 38 in that way, according to your mistakes, how much you made mistakes. Therefore, like I explained, and then you match, and then you see, and then still if you have any question, confusion, and if you think that I need to reevaluate, then I will be glad to work with you. Please let me know. I will do. Okay, so with that, this is fine. So, and then everybody just keep in mind. So, your next exam will be held in October 22. So, sometimes next week I will give you a reminder. October 22. That will be your midterm exam too. And then probably one more exam was scheduled sometimes in November. That is the midterm exam 3. Then what I will be doing, I will be picking up your best. For example, in on got you 90, you got 100 and you got 60, just random example. So of course, I will cancel your the lowest one. So therefore, this is true for everybody. So, and in that way, if you participate until exam 3, then you are covering the whole syllabus. Then again, there will be final exam, comprehensive exam that includes all the chapters, whole syllabus. I think the date is mentioned probably November 20 or I forgot, or November 19, something. That will be your, again, the final exam. Okay, and then after, soon I'll be covering something new for the DC motor generator. And then after today's class, I am going to assign you another set of homework, like homework set 4. You have returned homework set 3. I have still not graded, I will return you. But then I am going to assign you another set of homework soon today. And then you will be submitting in a week. So probably by next Thursday, you will be submitting it. So after the class, I will be uploading the homework first, and then I will be sending an email to make you alert that I have uploaded on eCourse. Okay, so then I am stop sharing here this one. And let me open today's class. Everybody now, can you see types of DC generator?
Yes, sir.
Okay. So everybody see, we are discussing that DC generator, DC motor together until last class. And we understood the working principle of DC generator, DC motor, but there are, varieties of DC generator. And then same thing goes for the DC motor. All of the applications, all of the types of DC generator goes for the DC motor. The same thing, same classification, same types. Now, here in the next slide, so everybody see, I have mentioned one type of generator, it is called separately excited. So I'm going to show you through a diagram. I will take you to the board and I will explain. And other type is called self-excited. So therefore, everybody, so two main classification. One is called separately excited and other in called the self-excited. So therefore, as you can see just by the name, separately excited means excitation means you have to excite the magnetic poles. So you all know that for both motor and generator, you need armature and you need a magnetic field. And magnetic field has the winding to excite those magnets. And that excitation is with the help of DC system. Now, how you excite it? Is it from separate source? Separately excited means there is a separate DC source, which is not the main or the applied voltage. This is a separate DC source. Accordingly, it is called separately excited. Soon I'll show you through diagram. And self-excited means you don't have any extra sources. First, you have to generate voltage and then use that generated voltage. That's why it is called the self-excited. And then under that self-excitation, this is the, the umbrella. Under this umbrella, there are several generators. One is called shunt generator. Shunt generator means field circuit is in parallel to the armature. So I am showing you that diagram. And then series generator. Sometimes it is called compound generator. And again, compound generator has several classification, like cumulative compound, differential compound, short shunt compound, long shunt compound. You see that there are lots of things. And then I said all of the DC generator types apply to the DC motor. This means same classification goes for the DC motor, exactly the same type. And then as I'm showing you through picture. And then residual magnetism, one term called, and then other term is called the field flashing. So what does that mean? So therefore, let me take you to the board, then it will be clear to you. Hold on. Okay, that first off, that separately excited DC generator. That is the first classification. So now let's have a look. So the first of all, that always I show this brief diagram, that this body is the armature, one is the coil is wound, and then you remember always I just show in that format, North Pole and South Pole. But instead of showing in that way, let me draw in terms of the circuit. How does it look like? Therefore, you see the two different circuit. Of course, this is the armature. Armature has coil and resistance. So this is on circuit, and this is the magnetic field. In fact, on the magnetic field, there is the coil winding, and then that winding is provided by the DC source. That is the meaning of that excitation. That's why, let me draw in that way. So you will be using this symbol to indicate that that is the armature. So let me go in that way. Okay. So this is the armature resistance, RA. So this means here I am representing this one, armature. And you see this is the coil. So I am not showing coil, but this coil has a small resistance, which is the RA that I am showing. And then these two symbols, this rectangular or rectangular box or the square box, those represent the carbon brass. You remember I was telling you that DC generator produces AC, and that AC is converted into DC with the help of the commutator. And after commutator, there is carbon brass, from where actually output is taken. That's why these two symbols, typically in the book, you will see somewhat very deep, fully this type of yes. This colored you will see, these are called the carbon brass. So therefore, when you will be drawing the armature circuit, you will be using this symbol from now. That will help you to understand the concept and your numerical problem. And then always you will be noticing there is two terminal like A1 and A2. So A1 and A2 indicates those two are the armature terminals. And this one is that armature resistance. Okay. And then we are discussing separately excited. So now I will be drawing that field circuit. So field circuit basically this coil. So therefore let me draw. So meaning that you see you have a coil and that coil has some resistance, which is that field resistance. So therefore this is the circuit for that magnetic field, north pole, south pole. So meaning that you are applying the voltage here, VF field voltage, and of course this is the DC voltage. This is your field current. That current is going. So therefore this is LF, inductance of the field, and this is actually your RF, field resistance, and that can be variable. I am putting a variable sign. So in the lab, when you will be doing lab number 7, lab number 8, you may need to vary that resistance, field resistance. That's why I gave the variable sign. So you see, this is the representation, or this is the representative circuit for that North Pole and South Pole. Therefore, that is the thing I was telling, that always I just show North Pole, South Pole, but in fact, that North Pole, South Pole is magnetized with this circuit. It is that inductance and this is resistance, and you are applying the voltage. Current is going. That current, that IF is causing, keeping it magnetized, keeping it magnetized. Okay. Now this arrangement, you see, in this picture, you see that, okay, and then here the voltage is generated. Let me write down here. You might write here, and this is your actually the terminal voltage. Say assume that if the load is connected, then current will flow. Okay, so this is terminal voltage for the generator, and this is the induced voltage. And after subtracting that drop IARA, that is your actually terminal voltage available for the load. So you see, everyone, this arrangement is called the separately excited, because, so can you see there is any connection between this stator circuit and this field circuit? Or let me level this one. This side is like armature circuit. This one is armature circuit. So left side is your field circuit. Okay. So therefore you see there is no direct connection. There is not at all any connection between the field circuit and armature circuit. Two circuits are separated. Especially this field circuit is separated. Accordingly, it is called separately excited DC generator. So therefore, how do you define this one? You will be telling that in case of a separately excited DC generator, field circuit is excited by an external DC source. It is not powered by this voltage. I mean, you might argue that, okay, I will be powering this one because it is DC. This is also DC here. I will be making connection here and here, but it's a separate source. Accordingly, it is called separately excited. Everybody, could you follow me?
Yes, yes.
Okay. Now come to the next category. You see, you remember next category was the self-excited. So now just for, I will not show this thing anymore. I will clean it. Now I am going to that, let me delete this one. I'll be going self-excited DC generator. This one. So what is that meaning? So now what I will do, I will change some this configuration. This circuit is fine. So now see what I am doing. Now can you see my connection? What I did, this is my that LF field circuit inductance, and this is my field circuit resistance. This means self-excited, for the self-excited case, at the connection point, I mean, at terminal A1 and A2, I just connected this thing in parallel, which was the field circuit. So therefore, what you are noticing, this is your field circuit, this portion. Let me write down at the beginning, then you will be fine. This is your field circuit. So therefore, you see, what is the source, how it is getting powered? There is no extra source now. It is fully dependent of this voltage or the voltage initially that is being built up, developed. It depends on that. So this means that the same voltage VT here, that voltage appears across this one. Accordingly, it is called self-excited. So therefore, can you see, can you just guess one possible shortcomings or limitation? That if there is no voltage build up here for some reason, then the field might not be excited. And if the field does not excite, meaning that you might get zero voltage here. Everybody, could you follow me? So what I am saying that you see the configuration. I mean, it might happen that there are some magnetism remaining or residual magnetism, then you are fine. So, okay, what I'm saying that if you see here, let's say this is time and then, sorry, this is your voltage, you are noticing the terminal voltage. And then according to this arrangement, you know that voltage is proportional to two factors. One is the flux, other one is the speed. You assume that, okay, it is properly connected to the shaft. It is properly connected to the shaft. This is spinning, no problem. But for example, there is no field current. No current is flowing. This is your field current. No current is going because even though it is spinning, it is not producing any voltage. Consequently, you see, if there is EF produced, then after subtracting that drop IARA here, and then only that portion will, oh, now I have to change that symbol. It is not here, so IA is now here. This is your IA. So therefore, EA minus IRA, that voltage will appear here. Now, if there is no voltage build up because there is no magnetism, so therefore, ultimately there will be no voltage. So that may be the drawback. So it may happen that okay, no, there is no voltage build up. It is the zero. But if it happens that there is some magnetism remaining, for example, today you make one experiment and already it was excited. And then next day you are making experiment using this arrangement, then initially you might get some voltage instead of zero, some voltage. And once some voltage build up, for example, you got 2 volt at the first moment, you just make this connection and you are taking a voltmeter here, you notice that there is 2 volt. So that is great. This means there are some remaining flux here. And then as that time increases, you are conducting experiments, then gradually voltage build up, field current is going and gradually getting excited. Next time your voltage increase, voltage will start increasing. It will go in that way. Now the thing is that, everybody look, if you notice that nothing is happening, you are always getting like 0 and 0. You are measuring, you are connecting a voltmeter here at this point and this point, but always you are getting 0 volt, meaning that this circuit is not working. This is not working because there is no remaining flux. This is spinning, the stator is, armature is rotating with the help of the shaft. One condition it means what the lack of phi. The field is not magnetized because this is dependent on that. If there is no voltage, it will not. It is called the self-excited. So if you always get 0 volt, then what you would do? You have to do this thing. You disconnect this thing. You first disconnect this one, and you disconnect from these 2 terminal, and then so I'm just showing, and then you connect to it just a DC source. You apply some DC volt for a moment. you connect it to a DC source, and then so that you make sure that the current is flowing to that field coil. Just for a few seconds, you just turn on this switch, DC voltage switch, and then this is called that field flushing. If you remember my previous slide, it is called the field flushing. So field flushing means that in case of a self-excited generator, so you see initially this was the connection. Everybody remember? Initially this was my connection, right? And so a minute ago, this was my connection. But when I noticed in case of self-excited generator, if I notice that no voltage is being developed, this means that is the lack of the magnetism. Its field circuit is not magnetized. In that situation, you disconnect it for a moment. You disconnect this one for a moment and connect with a separate source. Just excite the field. Just ignite the field. That phenomenon is called field flushing. After excitation, then immediately you make it connect. Again, you make it connect. Of course, you omit these DC sources. You don't need these things. You omit it and then you connect it back. Then next time, you will notice that, okay, you are getting some voltage. Everybody, could you follow me what I am explaining? Do you understand this on self-excited DC generator? It is called the self-excited because this is excited, the field circuit will be excited by the same terminal, by the same voltage. Now what I am saying that what if there is no voltage buildup? Because there might not be any magnetism. That's why for a moment you have to disconnect this field and connect with a extra DC source and then flush the field. Flush the field means just excite for a few seconds. And then you connect it back. And next time you notice that there is some voltage. And then because it is continuously current is going, so it is excited, it will build up voltage. So that phenomenon is called field flushing. Or it might happen that you don't need to apply the field flushing. Luckily, you might get like 1 volt or 2 volt at the beginning. Then why you may get that? In case there is some remaining flux or residual, the term is in case there is some residual, magnetism. This means on group did experiment using this setup and still there is some effect of magnet here. That is the reason with this arrangement at the beginning you might get some voltage. That is called the self-excited. So is everybody fine?
Yeah, I think so.
Yes. Okay, great. Now let me clean up. So again, I don't need this one. Now I am showing you another. So far you did separately excited, self-excited, and I don't need to show this one. Now I am going to that different thing. Instead of this connection, instead of connecting here and here, this means I disconnected this on sun field. It is called the series generator. Let me label that up. Series generator. Series generator means field circuit will be connected in series. So therefore, instead of here, the field circuit will be in series. So meaning that, let me clean up this line. So it will look like that. Also momentarily clean up this thing. Okay. For example, the main coil, this field circuit, field coil is here. You see, it is clearly in series. So this is your LS, the series field. And of course, you can assume that it has that resistance. So this is the main field coil. And it is connected in series with the armature. Accordingly, it is called series generator. So therefore, in this case, clearly you see, initially I showed that is the armature current. So the same current is flowing through the series coil. So accordingly, it is called series generator. So therefore, again, you see, so in this case, it depends on, therefore, you must spin this on, the armature should move, and only then it will produce some voltage, and then this circuit will work. Now, what is the motivation of this series generator or that previous connection? I mean, that parallel connection, which I said self-excited or the separate. It depends on the application. It depends on application. For example, for series type of motor is in most cases used in crane to lift up something, to hoist something, especially in crane, that series motor is used. They can provide very high starting torque. So therefore, it depends on the application. So different generator, different motor have different application. Accordingly, these concepts were built up. Now this is the series generator, and now this was the, it was called the shunt field. You will be noticing another term, shunt field. Shunt field means if the field circuit is connected in parallel to the armature, I mean that self-excited, that is called your shunt field. So therefore, let me connect it, this one. Okay. So therefore, now this is called the shunt field. This one is called the series field. Let me level here this one. This one is the series field. Now there is different type of generator or motor that have both series field and shunt field. I mean, this is the total configuration. That is called compound generator. That is called compound generator. Oh, sorry, let me explain this. That is called compound generator. Compound generator. So compound generator means it has both series field and the shunt field parallel. So this will be the structure. So therefore, easily you can guess that first voltage is developed, and this was the RA initially designated. This one is the armature resistance. So this is the IA current, and that current is divided into two parts. Something is going to that shunt field, and something is flowing to that series field, and ultimately it is going to the terminal. So this is called the compound generator. Everybody, could you follow me?
Yes, yes, I
Yeah, yeah, I can.
Yeah, great. So you see that gradually I am like making complicated. Okay. Now everybody say, now follow from here. Now compound generator can be again different types. One is called cumulative compound. Another thing is called cumulative compound generator. Cumulative compound generator means, now everybody see, because there are two field, series field and shunt field, it might happen that they are helping each other. I mean, they are helping each other means, you see that voltage production, EA is dependent on field, right? So yeah, voltage that is proportional to that field flux and then speed. So therefore, it might happen that series field and shunt field together, that is increasing the magnetic field strength. In that case, that is called the cumulative compound generator. On the other hand, it might happen, no, it looks like they're opposing each other. Series field is not helping shunt field, or shunt field not helping because it is creating one set of flux, it is creating another set of flux. They might be opposing each other. In that case, it is called the differential compound. In that case, it is called differential compound generator. I mean, the same configuration, but there might be two effects, either cumulative effect or differential effect. Accordingly, it is called cumulative compound generator or differential compound generator. Just it is the impact of the field, how they are they additive or are they subtractive? Are they helping or are they opposing each other? Depending on that, cumulative, differential. Okay, and then there are two more types of this configuration. The configuration as it is called the short shunt. Let me label at the bottom that one. Short shunt compound generator. As it is, this configuration, this is called the short shunt. Short shunt means this is the shunt field. That field is connected at these 2 points, A1 point and A2 point. Accordingly, it is called short shunt. But then there is long shunt. Let me write. There is long shunt. There is long. Oh, sorry. There is long shunt compound generator. So what is that means? So long shunt means this shunt field will not be connected here. That 2 point will be connected here. So therefore, let me a little bit clean up, and then I'm showing. Okay, so this means let disconnect this one. And this thing. Okay. So everybody see what I am doing? See my connection. I am connecting it here. So this is my actual terminal. Okay. So hold on. So here is my actual terminal, VT. So here this line, that is going to the load IL. Okay. Everybody now see my connection? What I did, I have that series field as it is. This is amplified. But you see, this was called the shunt field. So instead of connecting a on point all the way with the cable, I made it connected here. Because it is the like long distance, accordingly it is called long shunt compound generator. So what is the difference? Difference is that everybody look. First, this is the IA current, and then you see, because this is connected, the same current is going. After current coming here, something is going to the load, and then here it is going to the field, IF current. So this current is coming properly IA, or you can say series current, because this is series field. After coming here, it is divided into two parts. Something is going towards the field, and something is going towards the load. Because of this connection pattern, long distance, not this point is connected A on point, accordingly it is called long shunt compound generator. So therefore this means the previous diagram, if field would be connected here, then that is called short shunt, and if it would be connected here at this point, accordingly it is called the long shunt. Everybody, could you follow me? Is this fine? Like what is short shunt and what is long shunt? So once again, the short shunt is your previous diagram. Like once again, I omitted this one. When it was, you see, just okay. The field circuit is connected at the point one. You see, that is changing the thing. You see, IA current is going here. Equation is changing. You see, this is your armature current flowing, and after coming this point, it is divided two parts. Something is going to field, something is going to that series current. Sorry, the series field. And that is the same current that is going to the load. So that is changing the equation. And then instead of connecting here, if you would connect that on there, then that is changing your equation. You see, if you connect it at this point, that is changing the equation. Because now your IA current, same current is flowing through the series field. After coming here, it is divided. Something is going load, and then it is going to the field. So therefore, short shunt, long shunt, it is just changing the equation. Therefore, to solve the numerical problem, I mean, why I am emphasizing these points? Because we will be solving some numerical problems. That time you will be noticing that how the change of the connection changes in your equation and calculation. Everybody is fine? Do you have any confusion or question? Nathan, are you fine?
Yeah, I'm good. Sorry.
Okay, so okay, so therefore everybody please remember these diagrams, and then soon I will show you one example, then it will be clear. Okay, and then once again, that series generator, shunt generator, self-excited, separately excited, short shunt, long shunt, cumulative compound, different, all have different application. Each generator has different application. And again, all these classification applies equally to the DC motor. Again, they have different application. That's why they are a different arrangement. So therefore, now I am taking you to that place, and then I have this a cleaned up version. If you see that, just a moment. Okay, now see, I summarize these things, but then I also explained you what is residual magnetism and what is field flashing. And then in this slide, I am showing you those pictures. So those pictures are available in the book. This is figure 8.12. Currently, as I said, currently we are in chapter 8. You see, the very first one is that separately excited. The field is separate than the armature. And then as you can see here, again, the field is connected here. This is your shunt. Then next, see figure, this is the series. And then it is compound, both series and the shunt field. And then sometimes if you change the coil pattern, then your field direction might be changed, that is showing. And then this picture is for that short shunt. You see, these two are the long shunt. Can you see? Just now I explained. Connection is here. So therefore, these two pictures are for the long shunt. Okay, so therefore, I mean, because first time you looked, so it looks like a little bit hazy and complicated to you. Just everybody have a look on problem, and then it will be clear to you. Everybody, please read number 1, and then you try to solve it. You see, the armature current of a long shunt compound generator is 20 ampere. If the series field resistance, armature resistance, and shunt field resistances are 0.5 ohm, 0.9 ohm, and 5 ohm respectively, then calculate the generator terminal voltage, shunt field current, and load current if the generated voltage is 110 volt. Okay, so therefore everybody say the very first thing is that for this type of problem, so I must recommend you first draw a schematic of the long shunt generator. That will help you a lot. And then in that generator, you see what parameters are given and what is being asked, what you are being asked and what things are given. Then that will help you to solve the problem. So the question is, you calculate the generator terminal voltage and what is the shunt field current and what is the amount of load current. So therefore everybody, what I would recommend you, then again, let me take you the board and write down the equation, and then you come back to that. That will help you, because I think the long shunt is already there. So yes, this is our long shunt diagram. So everybody, please let me clean up. Okay, this is your diagram. So just a moment, let me something clean up. Okay. Okay. I think this picture will help you. Okay. Everybody, you first draw this picture to solve that problem. Everybody, please draw this one. This is the long shunt compound generator. So in the long shunt compound generator, as you can see, first you show this one. This is your voltage induced voltage. This is your armature resistance. And then this is your LS, but then also show the RS. So everybody say, even though you have the inductor in the circuit, but because this is DC, for DC, you know that inductor will be short. So LS has no effect. Same thing, you see, LF does not have any effect. It will be shorted because this is the DC. So main thing is the RF. Therefore, even though you see the LS, but please show the RS. So therefore, this RA is the armature resistance. This RS is the series resistance. And this RF is the field resistance. Now, let me write down the equation, then it will help you to solve the problem. So everybody say, what will be my VT expression? What will be the VT expression? So I am writing VT here. Look me. So for this configuration, VT will be your first induced voltage, EA, then subtract this drop, minus IRA, okay, and also you say again the same current is flowing, so therefore again there is another drop. It is still the same current, so then IA into RS. So RS is the shunt field resistance, sorry, series field resistance. RA is the armature resistance, right? So this will be your VT, you see, this point voltage. And everybody say, what is the value of the IF? Here I am writing. You see, so this means this is your field circuit. This means you are measuring voltage between this point and this point. So what is that voltage? Again, the same thing, right? This VT. Ultimately, that is your VT. So if you can get that VT, this means you're that VT over RF. That will be your IF equation. Everybody, can you follow me?
Yes, yes, I can.
Yes. So therefore look the equation and see that this is just the circuit and does it make sense? And then this is the wave. So therefore everybody please draw this diagram and write down these two equations, and then I am taking you to that problem and then you are ready to solve. Once you are done that you are done in this slide, then let me know. I mean this board. Draw this long shunt generator diagram and write down VT equation and IF, field current. I mean, ultimately, this is the IF, but I just showed it here. Oh, and then also, everybody notice what is your IL? What will be the value of the IL that I am writing it here? You see, IA minus IF. Write down this equation as well. IL, load current. How much is going to the load? So therefore, everybody say, here is it was my IA. It was series is still IA. After connecting this point, it is divided two parts, IF and then IL. That's why IL is IA minus IF. Or in other words, your IA is IF plus IL. So everybody please write down these equations. Then that will help you. Therefore, as you can see, depending on the generator, your equation will be somewhat changed. If it is like short shunt, if it would, then it will be little bit changed. So therefore, for every generator, your equation will be little change. I mean, that thing easily you can do because these are not too much complicated circuit. And accordingly, you have to solve the problem. Is everybody fine in this one?
Yeah, I believe so.
Okay. Then if you are done, and then I am taking you to that problem, provided that you wrote down all those equations. So now you all please see. Now everybody read the problem and solve it. Armature current long shunt generator 20 ampere. You see, this means IA value, armature current value is given 20. And you see all those resistances are given: series field resistance, armature resistance, Shunt field resistance. And it says generated voltage. This means EA value is given. 110 volt is the EA. Then calculate generator terminal voltage. This means find out VT, find out Shunt field current, IF, and find out the load current, IL. Can you right now calculate and let me know? I did not show it here, but my result is ready. You just tell me what result you are getting, and then I can check. Just everybody try this one, and then we don't have time. And then in next class we'll be solving number 2 and 3, and then few other things. I think here, let me write. So answer should be sorry, terminal voltage. Terminal voltage should be 82 volt. You check that you are getting that one. Field current, Shunt field current. Shunt field current will be 16.4 ampere, and your load current should be 3.6 ampere. Let me make red color. Yes. Everybody say you should get this result. Your terminal voltage, this means VT should be 82 volt. Your Shunt field current should be 16.4 ampere, and load current should be 3.6 ampere. Has anybody got so far, or still you are calculating?
Yeah, that's what I got.
Okay. So all three values are the same?
Yeah, they are.
Okay, great. Yeah. Okay, so therefore everybody keep trying. I wrote down the answers here. Everybody please try, and then you can see in the slides those long shunt, short shunt, everything given, or you might see that video that I drew on that whiteboard. So either way it will work, and then and then please try, and then everybody try to get this result. And then next class I will be discussing number 2 and 3, and then followed by other things. Okay, with that, I think already it is 11:10. Some of you have next classes. I would like to stop it here. Does anybody have any questions, comments?